Hey, this is Ken Rosever, and we're going to go over solving this radical equation here that's taken from the old Unit D test review that's posted online in PAL. All right, this radical equation is interesting because it has two radicals in it. So there's no way in one fell swoop to get rid of both radicals on both sides. So you have no choice but to go through a process one time of squaring everything and then going back and repeating that process again. So the first time through, you're only going to get rid of one radical when you square, because when you square both sides, you don't square each individual term, you have to square the whole side. And so when you square this, that cancels. You get x plus 8. But when you square this, you actually have to do x plus 3 plus 1 times itself. There's a shortcut to that, and the shortcut is you can square this. The square of the square root is what's inside. You can multiply this times this, so 1 times this is this, and double it, so you get 2 of those. And you can square that. That is the pattern for squaring a binomial. And when you've done all that, well, you see you still have a radical left over because the outer and inner terms matched, so you ended up with 2 of these 1 times square roots of x plus 3. So you're going to have to repeat the process. So let me move this over. Let me move this over. Actually, instead of minusing 3, minusing 1 individually over here, let me just put minus 4. That gets rid of all of these. And so now I'm to this line here. That's nice. Because those cancel out, I will not get a quadratic. I'll get something that is linear. And here I can divide by 2. I'm not going to divide by 2 here, even though I can, because I want you to see how you take care of this if this number is not a divisor of that number. So if this were like a 7 or something, you wouldn't want to divide out that 2 and create a fraction. You'd want to keep this 2 around. So here's what you would do in that case. You'd square this, you'd square this, you get 16 equals that, and you'd square each of these individually. So you get this times that. Square this, square this. Now I am going to divide out the 4 here, but if this 4 didn't go evenly into that 16, and it does because 2 went evenly into 4, if the 4 didn't go evenly into that, I would distribute it and solve it from there, but it does, so let me get rid of it. All right. But the big idea there is, again, when you square this, you square that, you square this. Squaring that gives you 4. Squaring the radical gives you what's under it. And then minus 3, you get 1. So it seems like the solution to this equation is 1. We don't get 2 solutions. If we did, we would check them both. And since we did square, we should probably check that this one works, right? Because sometimes squaring creates false positives. So 1 plus 3 is 4. The square root of 4 is 2. 2 plus 1 is 3. So when I plug in 1, this side comes out to 3. When I plug in 1 here, this side comes out to 3. Excellent. So the solution is indeed at 1. You always want to check your solution when you solve a radical equation and you have to raise both sides to an even power. What I'm going to do now is I'm going to solve the follow-up questions. So let me pull this off. And I'm going to set it to the side here for reference. Okay. To solve the radical equations that follow, and those are number 25, which looks like the same thing, only with that symbol. So the relation is now less than or equal to. And number 26, which is the same thing, but with a greater than symbol, you have two choices. You can do a number line, or I'm going to show you the graphs. Graphing is, we learn all this stuff about graphing, and then sometimes we don't use it like we could. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, whatever. And I think actually that's all I need. All right, so I have this graph that I'm going to use. I know that this is a radical function that's been shifted over 8. So over 8 is where it starts. It goes up 1 over 1, 1, 2, 3, 4, up 1, 2 if you want to be real accurate, and then 9 would be 1, 2, 3. So you'd get something that looks like this. This one here, this other side, is a radical function that has been shifted back 3, 1, 2, 3, and up 1. So it begins here, over 1, up 1, over 4, up 2. And you guys can see that those two functions, call this right side y1, call this left side y2, intersect at this point. Where is it? That point is at 1. That's the solution we got here. All right. Now, I'm looking for where y1, this is y1, this is y2, this is y1, this is y2. I'm looking here where y1 is below y2. y1 is below y2 before 1. Well, how long is it before 1? Not to negative infinity, not even from negative 8 to 1, but actually from negative 3 to 1, y1 is below. We can't say y1 is below y2 if y1 doesn't even exist. So the relevant feasible domain here, this one has a domain of x's bigger than negative 3. This one has a domain of x's bigger than negative 8. So the intersection of those domains is this. So that's where both graphs begin to exist at the same time. That is where any interval of solutions must begin. So our interval starts at negative 3 because that's where the first graph begins, and it goes to 1. y1 is below y2 from negative 3 to 1. Now this doesn't just say below, it says below or equal to. So is it below here? Yes, it is. So I'm going to include that point. Is it below here? No, it's not. But is it equal to? Yes, it is. So I'm going to include that value as well. Below or equal to. On this other one, we're looking where y1 is above y2. y1 moves above y2 after this solution. So we would go from 1. Oh, and I can't include 1 here, can I? Why not? There's no equal sign. So I'm not looking where y1 is equal to y2, which is at this point. I'm looking where y1 is above y2, which is right after this point. So those are your two solutions. If you wanted to solve this another way, you could use x-intercept method. You can move everything to one side, graph it with your graphing calculator, and look for where it's above or below 0. But the most important piece of solving radical inequalities is knowing where the domain begins. And if we have two parent functions, we have to go with the stricter parent. All right, so this one restricts things more than this one does. This graph doesn't begin until negative 3, so we can't compare values from two functions if both functions aren't existing. So we got to wait until both come into play. All right. Anyway, so that's it. Actually, I'll make one last comment here. Negative 3, 1. You could also do it by test points, but you wouldn't test any points beyond negative 3 because that's where the both functions come into play. So I hope that helps you guys out. Enjoy the video. Watch it in slow-mo. Repeat as needed. Bye-bye.